Hi, good morning, everyone. We're continuing with our last discussion where we have completed some basic concepts about carbocation and um, stability orders of carbocation, where we have seen some exceptions also. Okay, so in this class, we're going to observe the reactions of carbocation, all the possible reactions where carbocation is getting involved. We're going to discuss. First, we will talk about rearrangement. I am telling you the which things we are going to cover first. Okay. First, we will cover rearrangement. Rearrangement. Then ring expansion or contraction. Ring expansion and contraction. Part 1, Part 2, Part 3. Where we will be covering reactions with alkene. Reaction with alkene. Here we will be discussing five or six different type of reactions where carbocation is getting involved. Okay. Four, part four will be name reactions. There are few name reactions associated with carbocations. We are going to discuss them. So let's start with uh, rearrangements associated with carbocation. Okay. So part one, rearrangement. I will request you to write down what I am writing. Okay. So don't just listen to this class. Take a notebook and write them down. Okay. So that you can revise in an efficient way. When rearrangement will occur, if a carbocation is formed, when rearrangement will be formed, rearrangement will be occurring. Okay, if less stable, if there is less stable carbocation, then rearrangement will occur only if more stable carbocation is formed. Only if more stable carbocation is formed, then the less stable carbocation will be rearranged and will form more stable carbocation. There is a very much common confusion of students. If suppose there is a carbocation C plus, it is converting to C dash plus with rearrangement, which is less stable than C plus. But after that, if it undergoes uh, if it undergoes again rearrangement, then suppose C double dash plus is formed, which is more stable than C plus. Then C plus to C plus is more stable to less stable, but C plus to C dash plus to C double dash plus. C double dash plus is much more stable than C plus itself. Then will C plus convert to C double dash plus? Answer is no, it will not convert. It will not convert because each and every step you have to check that from less stable carbocation to more stable carbocation is forming or not. Okay, so be very careful with this and don't get confused. Okay, first let give me one example. Let me give you one example. Suppose this is beer, and I am giving here AgNO3, silver nitrate. We know from silver plus and beer, if they are associated, then they form AgBr precipitate. AgBr precipitate. Then what will happen? This carbocation will form. Carbocation can rearrange with two kind of process. One is hydride shift, another one is methyl shift. And two ways. By two ways it can rearrange. One is hydride shift, H minus shift, and second one is methyl shift, methyl shift. Now, which one is more prominent? Which one is more prone to shift? Hydride, if there is a competition, hydride shift versus methyl shift, then hydride shift is more preferred. Okay, this is a small atom. That's why. Now, this shift is only possible in adjacent positions, in 1 and 2 position, 1, 2 positions. From here, hydride can shift to its nearby position, not to the next to nearby position. This shift will not occur. So 1, 2 shift, always the shift is 1, 2 shift, not 1, 3 or 1, 4 for rearrangement of carbocation. Okay, so here the carbocation, that is 2-degree carbocation. Here is one hydrogen atom. Okay, so we can shift here like hydride shift 1, 2 position, and here also 1, 2 position. In left side there also 1, 2 position is there. If on right side 2 positions we make hydride shift, then H goes here. Then the carbocation forms at 2 position. So here hydrogen comes and here carbocation forms. So 2-degree carbocation to 1-degree carbocation. So this is not giving a stable, more stable carbocation. So this process will not occur. Rather, what will happen? This left side 2 position, this hydride is transferred there. Then the hydrogen is situated at here, and the carbocation will go there. This is 3-degree carbocation. 3-degree carbocation with C plus 2, 8 hyperconjugative structure. Okay, so this is more stable. So this process will occur. So this is the example of hydride shift with carbocationic rearrangement. But similar kind of reaction, if I give you, suppose this here, suppose this example with same reagent, what will happen? First, this carbocation will be formed. Then there is no hydride to shift. The methyl group, if shift, then what will happen? The methyl group comes here, CH3, this CH3 group, and the carbocation now in this position, from where the methyl position is dissociated. Okay, so this carbocation is now 3-degree carbocation. This was 2-degree carbocation. So here we can observe there is methyl shift. So in these two ways, hydride shift and methyl shift, the carbocationic rearrangement generally occurs. Okay, we are talking about rearrangement, rearrangement of carbocation, not ring expansion, contraction, etc. Okay, now, okay, so now if I give you some carbocations and if I ask that how many of them will undergo rearrangement, let's solve one question. You have to tell the number of carbocations which will show rearrangement. I am giving you some carbocations. Last one, class A, B, C, class D, E. So there are 5 carbocations given, and my question is how many carbocations among them will undergo rearrangement? Try yourself, and after that, let's take the answer. Take the answer. Okay. Answer is three. Three among them will undergo rearrangement. So that A, comma C, comma C. Let's see why. A can undergo rearrangement. If from this adjacent position hydride goes there, then 1-degree carbocation becomes 2-degree carbocation. Positive charge will come here. So 1 degree to 3-degree carbocation. The center will be 3 degrees. So rearrangement will occur. B, rearrangement will not occur. Why? If there are three adjacent positions, this position, if from here hydride shift occurs, then 1-degree carbocation forms. From here, 2-degree carbocation forms. From here, positive charge comes with hydride shift, then then also 2-degree carbocation is formed. But itself it is 3-degree carbocation, so no more stabilization. Okay, so this will not undergo. But C will undergo. C is 2 degree carbocation. From this position, if hydrate shift occurs, then it will give 3 degree carbocation. But from this position, this is also adjacent position. This will also give 2 degree carbocation. So this will not occur. This is giving this proton. Sorry, this hydrate shift is giving 3 degree carbocation. So rearrangement will occur from there. Four will also undergo hydrate shift or rearrangement. From here, if hydrate shift occurs, then 2 degree to 3 degree. This center was 2 degree cation. After hydrate shift, it will be 3 degree. So this is also undergoing rearrangement. Fifth, this will not undergo rearrangement because it is 3 degree. From here, if you do hydrate shift from here, there is no methyl, so we are not going to methyl shift. So these three hydrate shifts all will lead to 2 degree carbocation from 3 degree to 2 degree. So this is not stable enough. So this will not undergo rearrangement. So with this five example, we have clarified the concept that this shift will um, occur or not. Now, more than one step of rearrangement is possible. Suppose A is one carbocation, A to B. This is rearrangement. First rearrangement, carbocation rearrangement can occur if B is more stable than A. Only then. And then B to C rearrangement 2 can occur if C is more stable than B. Then only this will occur. But suppose C to D, this is rearrangement C. If D is less stable than C, this will not occur. Okay. For example, plus this carbocation. First, this will undergo rearrangement like this. This hydride shift. This hydride shift will give this carbocation. Then, so this shift occurs due to 2 degree carbocation to 3 degree carbocation. This is the stabilizing factor. After that, this hydrogen can also undergoing hydride shift because then the carbocation is forming. This is even more stable than the previous one. Okay, because this is getting mesomeric effect by this oxygen plus N mesomeric effect. So mesomeric effect gives much more stability than this. First carbocation was stabilized by 3 plus 1, 4 hyperconjugation. 3 plus 1, 4 hyperconjugation. Second one is getting stabilized by 2 plus 2 plus 2, 6 hyperconjugation. And next one is getting mesomeric. You know, mesomeric effect is much more prominent than hyperconjugation or inductive effect. So this one is much more stable. So two steps of rearrangement, more than one step of rearrangement is possible if, only if, the next rearranged carbocation is more stable than the non-rearranged carbocation. In every step, this should be followed. Okay. So our rearrangement is now complete. Our rearrangement is now complete. Next part we are going after that. Part one we have completed. Next part two, ring expansion and contraction. I am removing the annotation, clearing the board. Second, ring expansion and contraction. Our part two is the ring expansion or contraction. The ring expansion and contraction. Okay. So where ring expansion will occur, where not. Here the concept is again same. If the rearranged product, that means after ring expansion or after ring contraction, if the product is more stable than the starting material, starting carbocation, then only the expansion and contraction will occur. Otherwise not. For example, for example, suppose, uh, sorry. So here, okay. For example, four-member ring stability, four-member ring is less stable than five-member ring. Okay, if my carbocation is this plus, okay, then what will happen? This four-member ring, if as five-member ring is more stable, if this strange ring can undergo expansion like this, so this carbon will attach to this carbon. How will we draw it? Like this. Okay, this carbon is attaching to this carbon, and the bond of this carbon has been broken, right? And no, not another bond has formed there. So this position will have the positive charge. So this is basically a carbocation on five-member ring. So this will be formed. Now, if I have a six-member ring with CH2 plus, will this undergo same type of uh, ring expansion? If the ring expansion occurs, then we will be getting a seven-member ring with positive charge, right? Here, as here four-member ring with we are getting five-member positive, here six-member ring, and we are getting seven-member positive. Will this occur? We will say no, this will not occur. Okay. If why? Because five-member, six-member is more stable than five-member. Okay, and seven-member ring is less stable than six-member. Okay, six-member ring is most stable and most likely to form. Okay, so this will not occur, but this can occur. This can occur if we get some extra stability at this position. If we get some extra stability at this position, like if we add one OMe group here. In another example, if we add one OMe group here, OMe group means a group which can attribute plus M effect. So after rearrangement, we will be getting this OMe. Now, after this rearrangement, after the ring expansion, it is getting plus M effect of this OMe group. Plus M effect of this OMe group. So in this series, from a less stable ring, more stable ring will form. But reverse can also occur from a more stable ring. That is like this. A less stable ring can be formed if the carbocation gets plus M stabilization. Plus M stabilization like lone pair containing group like N, R2, sulfur, etc. So only in these cases, only plus M effect will lead to this opposite phenomenon. Another example, if I say you, uh, sorry, suppose there is a five-member ring and one CH2 plus. Will it undergo rearrangement to six-member ring plus? Yes, it will occur because in the series we can say six-member ring is susceptible to form from five-member ring after the rearrangement because it is more stable. Okay. If there is one OMe group, then it is more feasible. If OMe group is here and this OMe group comes here, so this is more stable. It will again occur, obviously. Okay. Now some different cases. Let's observe. Suppose two member ring are fused and this fusing position, there is one carbocation. This is carbocation. Will this undergo rearrangement like this? Mm, hydride? No, no, no. Can this show ring contraction? My question is, can this show ring contraction like this? This is a ring contraction, right? 6 member to 5 member. Will this occur? No, this will not occur because 6 member ring is more stable. So from more stable ring to less stable ring, no question to form. But if we give one stabilizing group like OM or OH, for example, positive charge OH suppose. Now this when this ring contraction will occur. Why? After this contraction, let me draw. It have positive charge, but there is one OH group. OH group has oxygen lone pair will give plus M effect that will stable the carbocation very much. Because the less stable ring is forming. So here the less stable ring is forming, but the stability arising due to clustering effect of OH group is overcoming the instability by ring contraction. So in these cases, ring contraction also may occur. Okay. One more example. Plus. This is 7 member ring carbocation. What will happen for it is already 3 degrees. So if you do methyl shift, then it is also 3 degrees. So one option left here is the ring contraction. We know 6 member ring is more stable than 7 member ring. So one option left here is ring contraction. From this side, if ring contract, then from this side, why this side, not this side, you will get to know. From this side, mm, this will form. But from this side, you will not getting a 3 degree carbocation. After ring contraction, you can draw and you can check. So this is ring contraction. So ring has attained more stability, and again the carbocation is 3 degree carbocation. So this will occur, and this will give to ring contraction. So till now we have observed the ring expansion and ring contraction, both the things. Okay. Now I have a one question to you. Question is rearrange if possible. Rearrange if possible. I will give you carbocation. Okay. And if rearrangement is possible, you have to do that. And you have to say what is final product. One more thing I want to say. In carbocation, what is the final fate of the reaction? If any nucleophile is given, then the nucleophile will attach the carbocation and we will be getting a nucleophile over there, over this position, this carbocation position. But if nucleophile is not given, then what will happen? Then elimination will happen. Hydrogen will get eliminated. For example, from here the positive charge and this hydrogen suppose this will undergo elimination and double bond will come over there. Okay. If we get positive charge at this position, then this more stable alkene will form. That is TGS product. Okay. So we will be seeing that reaction when we will be going to the name reactions and reactions of alkyl. Then we will see that. Now my question is, this is our carbocation. Will it rearrange? And if it undergo rearrangement, then what will be the final product? The answer is yes, it will undergo rearrangement. How? This 4 member ring, positive charge, 4 member ring. For first example, in this example, You can see four-member ring, and then after one carbon positive charge. Here you can also see this is four-member ring, and after one carbon there is a positive charge. Okay, so the same type of system. Okay, so we can expect the ring expansion over here. Suppose ring has expanded. So what will happen? This four-member ring as it is. Now, this first question, the system we had, we are getting again the same system like this. Four-member ring, then after one carbon there is one positive charge. Same type of system we are getting, right? So, now this can again undergo ring expansion. Oh, sorry. Then these bonds I am drawing like this. Another thing I am drawing as it is. Okay. Then this ring like this, and the cation will be forming there. This is the carbocation. So if we write it in a proper way, then this is nothing but two five-member rings fused together. Okay, and there is one positive charge. If nucleophile is given, then nucleophile will attach there, and if not given, then the hydride from here will make it a double bond. Okay, why this double bond? There is more hydride and the alpha position of the carbocation. There are three alpha positions, so three hydride, three hydrogen can make this double bond. So here, here, or here. So you have to look upon more stable positive, more stable alkene. Okay, this alkene will be more stable. You have to count the hyperconjugative structure. Then you will be getting the more stable double bond forming here. So this is a rearrangement. Okay. Again, this same type of rearrangement possible if I give you two five-member ring with positive charge over here. Then you will be getting similarly two six-member rings used together. Right. In the same way. Because this rearrangement will occur. So now you can understand the ring expansion versus the ring contraction. But if I give you two six-member ring in this way, will this undergo ring expansion or contraction or anything? The two six-member ring, will this form two seven-member rings fused together? Seven members. Carbocation. No, this will not be because seven member is less stable than six members. But if we give one mesomeric effect group which can show mesomeric effect attached with that, so that after rearrangement it can attain mesomeric stability, then it will occur. Okay, so this is the thing. These so part two we have completed rearrangement and ring expansion contraction. Then we will be starting addition reaction. Okay. Mm, no, no, no. Before that, in these ring expansion and ring contraction, we have seen the carbocations are formed. I have started with carbocations, but we have to look upon which reactions generate carbocations. Okay, so there are two reactions associated with it. We are going to cover that. First one is the dehydration of alcohol. The carbocation, how the carbocation is formed? First, the carbocation will form. This is a reactive intermediate. We have to know the reaction associated with it. So first we have to look upon the reaction from where carbocation can be generated. Majorly there are two cases where carbocation can be generated. I'm clearing this one. There are two ways mainly from where carbocation can be generated. Okay. First, we can write T here. Okay. First way I have already shown over here that something halide. and Ag plus cation, silver nitrate like thing. So this will give AgBr precipitate and thus carbocation will form. So first way of making carbocation. Second way is dehydration of alcohol. Dehydration of alcohol. Uh, from dehydration of alcohols like this, OH. And if you are giving H plus source, for example from H2SO4, HCl, H3PO4, etc. So oxygen here is nucleophile and H plus is electrophile, then it will attack. We will be getting OH2 plus, and very simply water will remove and we will be getting this positive charge. Okay. If nucleophile is given, nucleophile will attack there and we will be getting nucleophile. If nucleophile is not given, then alpha hydrogen, okay, so this will make a double bond. So this will be fate of the reaction. Right. Third way is third way diazotization. 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 We will be discussing it. Ah, okay. Before that, first way you know, second way I am discussing in a little detail. Okay. Question. First question. Phenyl CH2 CHOH. We are giving H plus. What will happen? We know from following this way, carbocation will form where OH is there in the position of OH. pH. This now, when carbocation is formed, we have to look upon the possibility of a ring expansion contraction or rearrangement. Here we can see there is no ring, so no question of ring expansion contraction. So let's look at rearrangement. This positive charge, uh, uh, beside this positive charge, there is one hydride shift from this position can occur, or from hydride shift from this position can occur. If hydride shift from this position occurs, then we will be getting 1 degree carbocation. Obviously, it is not going to form because from 2 degree to 1 degree it is not feasible. But if we make an hydride shift from this hydrogen, what we are getting pH this positive, and then the hydride comes here. Okay? This hydride comes here. Now we can see this is benzylic cation pH then plus. pH means phenyl ring. It can undergo resonance. Okay, plus CH2 CH2. This is the carbocation. So this is the case. Okay. So what will happen? Uh, no nucleophile is given, so the hydride will make it positive charge. Okay. Sorry, the hydride will make it alkene. This another isomer is possible. This is I have drawn trans. This is also possible, but trans is more stable, so this will be major. So styrene type of compound is formed. This is a major product. So this is how we have to approach. Okay. Now next question. Similar type of question I will be giving you as homework. Okay. Do yourself. I will be giving you answer and question. OH H2SO4. What will happen? Okay. I am giving you the answer and you have to try yourself after rearrangement, etc. if occur or ring contraction, expansion, etc. This will be major product. Do yourself. Next question I'm giving to you. OH, H plus. Now you know that if here positive charge comes, then how the rearrangement occurs, the ring expansion, two times ring expansion occurs, and what will be the fate of the reaction after that. So this will be giving us product. This. Do yourself all the steps, show mechanism, write down the mechanism, and come to this final product. Okay. Now there is a question, a little tricky. Okay. The question is, oh, H plus. All the questions I'm giving you, these are from different standard reference books. Okay. Um, so I have my copy where I have noted down this specific example. From there, I am giving to you. So what happens here? If first step, the carbocation, simple carbocation will form. You all know this carbocation will form from water removal. If you do this, hydride, if you shift there, hydride shift, then what you are doing is a mistake because this system is now anti-aromatic. This is a very less stable, so this is not going to form. Rather, what will happen? Ring expansion will occur. This ring will expand there. After the ring expansion, just draw like this. Draw like what I am drawing. Draw as it is. Okay, now this bond is breaking. Okay, this bond is breaking and this carbon is connecting to this center. Okay, now this center will get positive charge because this bond has broken and this carbon is making a new bond, but this carbon is not making any bond because it has broken the bond only. It has not formed any new bond. This center will have positive charge. Okay, and then double bond here, double bond here. Okay. Now write down in a proper way. There is six-member ring, double bond, and then positive charge. Now you know that no nucleophile is given, then very fast this will undergo elimination like this. So final product is our very much favorite compound, benzene, very much carcinogenic compound, benzene. Benzene is carcinogenic, it causes cancer. When we used to uh, perform some experiments with benzene in our lab, then what we have to do, we have to wear hand gloves. In normal reactions, we don't use generally gloves, but also it is suggested to us to wear gloves for every reactions in lab, but we generally don't do that. But this is very much carcinogenic, and we must use gloves and mask before reaction with benzene. Now, similar type of question. Now, this type of questions you are familiar. So one question you again do yourself, and I will be writing the answers as well. Okay. If you face any problem, ask me in the comments. Mm, what will happen? This five-member ring, OH five-member ring, H plus. Try yourself. The product will be similar to the this question. Okay. Okay. Now another question. What will happen if there is one bridge compound? There is carbon. There is no. Let's say carbon. Okay. There is a bridge to methyl, and in endo position there is OH. This is exo position. Outer side this is exo position, exo region. The group in this region above side is exo position. The hydrogen here is exo position, but OH in the below side this is endo position. So what will happen if we give H plus over here? Okay. First, obviously, water will form, then carbocation will form. Carbocation is forming, and there are two methyl groups. Okay. If hydride shifts from here, okay, this is 2-degree carbocation, right? If hydride shift occurs from here, then the carbocation we will be getting will be this. And you very much know bridgehead carbocations are very much unstable. This bridgehead position carbocation is very much unstable, as I've discussed earlier, due to Braid's rule, BREDT, surface Braid's rule. Okay, so this hydride shift will not occur. Rather, what will happen from the another side, methyl shift can occur. Yes or no? From here, this methyl can shift here. So this will be giving methyl, methyl. The methyl is going to positive charge. After that, no nucleophile is given. So we have to make the alkene. Now, there are three alpha positions of this positive charge. This position, this alpha position, this alpha position, this alpha position. From where hydrogen will go? This hydrogen, if it goes, that will make positive charge here. This hydrogen, if it goes. If this hydrogen goes, will make positive charge there. If this goes, this will make positive charge here. Right? So what will happen? If let's draw the three cases HA, HB, HC. If HA gives the hydride for alkene formation, then the alkene will be getting this. Second one is HB will be getting this double one here. And last one HC, for HC we will be getting. Second will not occur because in bridgehead position there is again sp2 carbon, double bond means sp2 carbon. Bristol says bridgehead position sp2 carbon is not possible. Okay, carbocation is sp2, that's why carbocation is not formed, and again alkene, this is also sp2 carbon is not formed. And competition versus this one and this one. The above one, this has 3 plus 3, 6 hyperconjugative structure, 6 hyperconjugative structure, and below one, this will have one hyperconjugative structure. So this wins, and this will be the major product. And let me tell you another concept uh, of this alkene. Okay, let me draw over here. If it is asked that number of hyperconjugative structure possible, then you can see there are four alpha positions: alpha, 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 alpha. There are three alpha hydrogen. There is also three alpha hydrogen. This is one alpha. This is one alpha. This can't show hyperconjugation. If you draw hyperconjugated structure, then you have to make double bond over here, bridgehead position. So this is not possible. So these hydrogens cannot show. These are alpha hydrogens, obviously. These are the exceptional case of alpha hydrogen. I will not say exceptional, but a tricky part of hyperconjugation. That always the number of alpha hydrogen is not equal to number of hyperconjugative structure, because these two alpha hydrogen cannot show hyperconjugative structure. Okay, because bridgehead double bond position, this is very much unstable. So only these 3 plus 3, 6 hydrogen will show hyperconjugation, and 6 hyperconjugative structures. You will get 6. And here also you will get one from this. This hydrogen will not show hyperconjugative structure, will not contribute in hyperconjugative structure. Okay. I hope it is. I hope it's clear to you. With one last question, let me clear this session. Let me end the session. Uh, okay. The last question is six-member ring OH. We are giving H plus, and another one H2 OH, H2 OH, H plus. First reaction, rate constant is K1. Second reaction, rate constant is K2. Which reaction will uh, will be faster? Which reaction will be faster? Okay, it will be faster. K1 will be faster. Why? Always remember, carbocation formation step is RD step, the determining step, not rearrangement step. Rearrangement step is not RD step. So if rearrangement occurs, that step will not be RD step. Rather than carbocation formation step will be RD step. So from first one, the carbocation will be getting uh, will be a primary carbocation. The second one, the carbocation form, it will be 3 degree carbocation with 3 plus 2 plus 2, 7 hyperconjugated structure. So K2 rate will be more than K1. Okay, I hope it's clear to you. In the next class, we will be discussing the second way, that is diazotization. Second way of formation of carbocation, and after that, I will be giving you some questions of rearrangement. Okay. After we complete diazotization, we will be moving towards the reaction of alkene and alkyne. Okay, reaction of alkene and alkyne, where carbocation is formed. There are many reactions in that section. H plus water addition, halogen acid addition, H2 addition, NBS addition, BH3 addition, oxymercuration, demercuration, all of these reactions we are going to see step by step. Okay, in next class most probably we are going to discuss. So before that, I hope this lecture is helpful to you. And if you have any confusion in this lecture, you can ask in the comment. Thank you. Let's meet you in the next class with much more reactions, much more content. Okay. Thank you.